Done, sir. We can begin now.
Is it live?
Yes, sir. It's live.
Okay then. Good morning, learners. I hope I'm audible, visible, and there's no problem in the sound or in the video. You can just get some confirmation. That would be good. I hope I'm audible, visible, and there are no problems with the sound or the video. Good. Thank you, Kunal. So you'll find that I have shared with you a particular link. So this link will take you to a folder where there's a specific Python file which is there and a data set which is there. What we are going to do today is that one, obviously we will continue with our learning, and two is I'll probably show you a decision tree model, the regression model from end to end. Now what I've done is this particular data set which is there, it's a cleaned data set, which means that you don't need to clean it further, so that we can directly jump onto the modeling part and can probably save some time out there. Also, like I think I had told you in the last session, and even in the course mapping, it is given that there's a software which is there. It's called the Orange Data Mining Tool, which I had asked you to download. So I hope you have downloaded that, because again, if you have downloaded that, it will be nice if we can show that the demonstration that software also. So people who are probably a bit jittery with Python, so tool like this, they can probably find themselves at home, right? That's what we are going to do today. In the meantime, before we start off with the session, any specific expectation that you are having, if you can just put it onto the chat. So what I'll try to do is I'll try to ensure that whatever expectations are there, we are probably able to take it up in the course of our learning session. So Prashant is asking that where can we find it? Prashant, in the document which has been shared with you for the LS topics and the mapping, you'll find the link to that particular software is there. The last class also, I think I asked many people that whether they have installed the software or not. What I understood is that I think many of them, they have not installed. So yeah, I am hoping that today you would have installed the particular piece. Right? Okay. So let's move on to the decision tree, the particular topic of decision tree. The last class, we were actually discussing that how you are creating decision tree models. And typically, we were focused on the classification model. So again, just to show you in a small nutshell how we do decision tree. Very simple, very easy. Step one, read the data. Step two, you segregate. Features and target, right? Step three, pre-process the features. And then step four, find out the most important feature for splitting. The part, I think, where there was quite a bit of confusion that how we are finding out the most important feature for splitting. Very simple. What we are doing is that mathematically we are trying to find out that across all the variables which are there, which of the variables impact the maximum fitting the model when you're doing a splitting. And the first one that we used was something called a chi-square. And then we talked about classification error, Gini index, and then entropy. These are some of the techniques that we have discussed in last session. Again, I'll come back to the learners now. Any particular doubts, questions that you are having before we move ahead on this particular part? If something is not clear on this particular part, please raise your hand, sound out your concern. Because again, if you are not understanding it here, maybe you will not understand it going ahead also. Okay, Shans is asking, can we help understand the entropy today? Fair enough, Shans. We'll do that. Anyone else? Anyone else? Anyone else? Kunal is asking the chi-square. Okay. Okay. Gini index. Very good. Okay. Anyone else? Anyone else? You mean all? Okay. So yeah, what we'll try to do is we'll try to create, but again, learners, please ensure that whenever you are coming to the session, async content, you are covering that. It's explaining the async content. The class is mainly for the doubt clear part. So I'll go to that particular part. But again, for the sake of the coverage and for everyone's convenience, I'll request everyone to come to the preparation well. Right? Okay. So let's go back to this particular part. Firstly, the mathematical note, chi-square. So for chi-square is observed minus expected whole square by expected. Observed is the value in the data. Expected is the value. I repeat, expected is the value which will be there if you assume that all the classes are equally like. So let's say that you have 10 rows of data. Two classes, true and false, right? So then in this 10 rows of data, let's say 7 are true and 3 are false. And then let's say there are several features which determines when is something true, when is something false. So my observed value will actually pertain to the features feature 1, feature 2, and let's say the target. So as I said, true, false, true, 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 false. So let me take not 10, but just for the sake of your understanding, 6 rows of data where we have four and false cases. And this feature target, say, on default. These features are, let's say, one of the feature is education, graduate, undergraduate, graduate, 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 and graduate. This is one of the feature. Feature 2 is high salary. Make one change. High salary, low salary, high salary, high salary, low salary, high salary. Let's see the features, and based on feature, whether someone is a graduate or not, and whether they have high salary or low salary, the target value, which is the low default, that particular thing is a decision tree, so that someone who's probably having similar kind of data, they're able to figure out that when is that someone defaults on the loan and when is that someone true on the loan. Right? Let me do one thing. Let me come to the first variable, which is the variable called feature 1. Feature 1, we have two values, graduate and undergraduate. And here, if I see for the graduate cases, true and false. Here we have 3 true and 1 false. For the undergraduate case, we have 1 true and 1 false. What we have, right? Now, if I would like to calculate the chi-square values, in the first case, for the graduate true case, here there are 2 classes. So these are my observed, but my expected is 2 here and 2 here. For the undergraduate, this is observed, and my expected is 1 here, 1 here. Right? The classes which are there will be equally divided between whatever are the different classes in the same proportion. Right? Based on this value, I can actually find out the chi-square value, where in the first case my observed is 3, while my expected is 2. In the second case, my observed is actually 1, while my expected is 2. In the third case, my observed value is 1. The expected value is also 1. And in the fourth case, once again, my observed value is 1 and the expected value is 1. So summing all that up, I get my total chi-square value for feature 1. Right? Question from someone? So Kunal is asking, how did we arrive at the expected value of 2? Kunal, I have repeated it. There are 4 examples for the graduate cases. Observed is the one which is the actual distribution of the 4 cases, but expected is the one which is that the number of classes which you are having here, the classes are true and false. That's the denominator, and the numerator is the number of cases that you are having. So here in the first case, when you had 4 cases, you're expecting that 2 of them will be true and 2 of them will be false. You're assuming that this particular variable feature 1 did not have any kind of impact. So if my observed and the expected they are the same, then that chi-square value becomes 0. Right? That actually happens in the undergraduate case. Only 2 cases are there, and observed and expected they are the same. that particular case, chi-square value for the undergraduate case is 0. Now is asking from the business decision. Yes, it is from the business decision or with the target variable. Here we had this target variable. It's the distribution of the target variable which we are talking about. Right? So now we can calculate the chi-square for the feature 1. Similarly, let's calculate the chi-square value for the feature 2. So for the feature 2, what we can do is we can take the feature 2, which is the high score, high salary and low salary. Let's see observed and let's see expected. For the high salary cases, total number of cases are 1, 2, 3, 4. 4 high salary cases, so 2 low salary cases. Observed value for the high salary cases: 1, 2, true, 2, and false. 3 true, 1 if. But the expected is once again 2. And for the low salary cases, what is happening is that low salary, false and true. 1 false, 1 true. Here also expected is 1, 1. From this, once again, you can find out the chi-square value for the feature 2. This particular case, in this particular example, you'll find that both the chi-square values are the same. So either of it be used for doing the splitting. But again, if you get a case where the feature 1 chi-square is more than that of the feature 2 chi-square, then in that particular case, you are going to use the one which has a overall higher chi-square. I hope now the point is clear to everyone. Right? So again, the best part is that only for your understanding purpose. Like most of you are managers or you're going to be managers. For your part, what you need to do is, again, you need to just understand what's the underlying model which is running behind it and how the splitting and everything is happening. Most of it is already done by the system. So you don't need to worry much about how the results are calculated, but you need to interpret the results which are there. I hope I'm able to make myself. Okay, now it's asking what's the interpretation of this chi-square. As I said, high chi-square better for splitting, low chi-square not preferred for splitting. Again, the root is into the mathematical theory. Again, we are not going deep into mathematics. We are explaining that, okay, how it's coming. And again, once you get the chi-square values, how you're interpreting the chi-square values. Try to get the roots of, again, why it is happening like that, why high chi-square is better, chi-square is better. Again, how the chi-square values are leading to the probability distribution, we probably have to cover that. We are not doing it because, again, that's not the scope of what we are learning. Right? Anyone else? Any particular question with this particular regard? Anyone else? Yes, Dinesh, you are completely correct. Where chi-square is 0, so that is pretty bad for doing splitting. Right? So yeah. See, and when what we do is we take in the indicated chi-square value of a particular feature, and then we match the indicated value of feature 1, chi-square feature 1 with the indicated value of chi-square. Whichever is higher, take that for split. That's what we do. But again, as you have rightly said, that if the chi-square value is 0, which means that there's no point in using that particular feature for splitting the bill. Right? Here Dinesh is asking that we can say the expected and the actual is matching. Doesn't that mean that we are getting what we expected? Okay. In this particular part, if you have studied equation, the expected part is feature does not have any impact. So this is the assumption behind the expected part, that whatever feature I am considering that does not have any impact in your final part. So let's say, let me give a very trivial example. Let's say I take all the data of people who are registered for this particular MBX, and then what I do is I take out the people who probably attends this LS sessions and people who doesn't attend the LS session. Now at the end of the day, I would like to find out that whether the people who are attending the LS sessions, they are indeed doing better than the people who do not attend those LS sessions. So for this, I'll first observe the values. Okay, for people who attended LS sessions, how many of them got very good, average, and poor? People who did not attend the LS sessions, how many of them got very good, average, and poor? And let's say that there are 90 people in the class. So my assumption, which actually gets me the expected part, is that irrespective of whether you are attending the LS sessions or not, performance will be the same. In that case, what will happen is that whatever is the observed, let's say LS sessions, we are observing that of those 90 people, so we are observing that very good score, let's say 60 of them they are making, average 20 they are making, and poor 10 of them they are making, giving a poor score. So that's the observed one. But the expected one, which I'm saying, is basing on the assumptions that it is immaterial whether you attend the place or not. So you have an equally likely chance of getting all the three. The expected would be 30 here, 30 here, 30 here. The 90 people divided equally between these three classes. And then when we are actually calculating the chi-square values, depending on the chi-square value, will determine that whether this particular part attended this LS or not had any impact or didn't have any impact. So let's say that if my values were not 60, 20, 10, rather it was 30, 30, 30 only. My observed and the expected, they matches. Chi-square value becomes 0. So which means this particular feature, LS, does not have any effect on whether student is doing well or not in those final exams. Even if it was something like, let's say, this is, let's say, 31, this is 29, and this is 30. That is also chi-square value is very small. So probably we are going to look into the other things like, okay, how much time they have devoted. Significant amount of time, not significant amount of time, no time at all. How many of them probably did the async content class? Right? So things like this. Okay, I hope now you have been able to understand the observed and the expected one. Dinesh, Simanti, all the other people, I hope the observed is the expected is clear right now. Right? Okay. Let's move on then. Let's move on. Coming back to the popularity of decision tree, one part is no domain knowledge required. Very important part. Right? Domain knowledge is not required. Just by doing this mathematical manipulation, you can actually find out that which particular variable impacts particular decision process, which variable doesn't impact the decision process. Easy to understand. So once you have understood the underlying principle logic, it's pretty easy to understand. You can use decision tree for doing some kind of a data exploration. That's a part about decision tree. Less data cleaning required. Right? One of the few algorithms which is very robust, missing value, can handle all the different kinds of data. Right? Can handle data like the categorical data, numeric data, binary data, all the different kind of data it can handle. Right? So those are the reasons why this particular decision is pretty popular. It is one inherent problem of the decision. See, like what you can do is you can split the decision tree. Like I'll show you the image from the last class. First, how our final tree look like. And when we did the splitting, the final splitting, remember here there were only one records left, right? If you remember, here we were only one records left or determine the transportation mode decision, right? It could have been either on the car ownership or on the what? That if the data volume is not significant, it can lead you to some terminal nodes which are very sparse, only one record. Having just one record in the terminal node is probably not a very good indication of a model process. It becomes more like a rote learning, right? Say, for example, we are discussing few things in the class. If you remember, when you are being taught in school days, the teacher taught something in the class, went back to your home, based on the learning which the teacher gave, you tried to solve the chapter end examples, and then you are able to see that okay, whatever you have written, whatever you found out the answers, does it match with the answers at the end of the book or not? If it matches, your learning has been good. If it doesn't match, then probably you have to revisit your learning. And then I think you also remember there were some people used to call them rattu. What they will do is that whatever the teacher has taught, line by line, heart by heart, they will probably memorize each and every point of it. So if the points are coming from whatever the teacher taught, they will probably do an excellent job in the exam. If that's not the case, it's something application based, if it's something which is closely associated with whatever was being taught, but not exactly, people fail. Right? So remember the movie Three Idiots, right? Chatur Ramalingam. Completely, he was a bookworm. So whatever was there in the book, he knew the point of it. If there was something which was coming from outside, he used to not perform. That's why in the exams, he was always the second best and never become the best. That's one of the problems with decision tree. Sometimes it actually, rather than treating a model, it memorizes the data. That's where the problem is. Rather than memorizing the data, actually create a model which can give. Right? That is when the process of overfitting and underfitting comes in. So underfitting, when does underfitting happens? Is when you make very easy and trivial assumptions about a particular topic. So let's say you have been taught basic things like addition in the class, and you will only assume that, okay, whatever happens, there will be only addition problem for digit numbers, and I'll do extremely well. But again, the very fact that you have been taught addition can be given 2 digits, 3 digits, 4 digits, any number of digits to calculate. Your learning has been stopped only till those, let's say, 2 digits or 1 digit, then that's an underfit model. You have learned very less about what is expected for you to perform. Underfit part. Let's come to the other part, which is the overfitting part. What happens in the overfitting part is that you have not actually understood how does addition happens. But whatever was being taught in the class, so 2 plus 7 is let's say 9, 3 plus 8 is 10. Everything you have memorized. Everything you have memorized. Now, if you have been asked to solve a problem similar to what was already taught to you, you are getting extremely good results. You already have in your memory what was there, and then you are directly saying that it's the answer. If you have only memorized the answer, but not really understood how to arrive to the results, you will do extremely well on whatever has been taught in the class, but in some unknown problem, your model will do extremely bad. That is the overfitting part. Right? I hope everyone understood what's overfitting and underfitting. And typically in a decision tree, overfitting is a big problem you need to probably solve. Right? So typically, this is how a decision tree model gets created. One is the data is there, you split the data into a training part and a testing or a validation part. And then in the training data, what you do is that you recursively you work on the training data, build the decision. They use things like this information gain, right? Gini index, all those things. So by the way, I think someone also asked that what is the information gain? What is the Gini index? Entropy, if you remember, entropy comes from the Gauss theory in physics. It's expressed as minus log to the base 2 proportions of the different classes multiplied by the corresponding classes. Pi log to the base 2. Both the classes, they are equally likely entropy value will be 1, which means maximum impure. If one class is the majority, other class is the minority or 0, entropy will come as 0, which means minimum impure or the pure good. So in the previous example, right, the example which I was trying to give, right, let's say this learning sessions, people scoring good, average, poor, and then actual. If I see learning session people are attending, let's say all of the people who are attending the learning session, they are getting good results, no average, no poor. So which means that if I look into the entropy of this particular learning session variable, entropy is equal to minus pi log to the base 2 pi. So minus 90 by 90 into log to the base 2 90 by 90. Log 1 is 0. So entropy here will be 0. Which means that this is a pure. If, by the way, happens in the other way, let's say, let me just remove one of the this thing, good and poor. Let me just work with 2 of them. So let's say that in both the cases, what is happening is that your entropy value, let's say 50 good, 50 poor is what you're getting. That particular case, entropy value comes as minus 50 by 50 log to the base 2 50 by 50 minus 50 by 50 log to the base 2 50 by, which by the way comes out as 1. Maximum impurity. Whether you attend the LS or not doesn't have any bearing on your performance. That was how we calculated the entropy. Right? Kunal is asking the underfit and the overfit in terms of the best fit line or curve. Kunal will come to this when we talk about the model selection part. Right? It will be covered out there in details. Right? For the time being, just understand that what it means. We'll come to that in more details. So Kajal is asking, is there any range for entropy? Yes, Kajal, the range is between 0 to 1. So 0 means least impure, which means a pure node, and 1 means maximum impure, that there is no impurity. Come back to this example. If you attending this LS did not have any bearing on your performance in the exam, both are equally likely. So 100 cases were there, and people who attended the LS, 50 of them they got good scores, 50 of them they got poor scores. No bearing, no bearing. So LS is actually a very pretty bad measure, LS attendance, for your performance. But again, if the same thing was 100 here and 0 here, then what will happen is that the entropy value will come out as 0, which means what? That is a very pure node. So there are probably other features also, right? The amount of time you spend, other features also. But again, if you are getting a feature where the purity is very high of 0, which means that only solves a particular purpose. If you are using just this particular feature called LS attendance, that is completely helping you understand, take the decision that whether doing well or not. Right? Entropy equal to 0 is a pure model. Yes, entropy equal to 0 means not a pure model, Kajal. Entropy equal to 0 means that particular feature is a pure feature. If you use that particular feature for splitting, you are good. On the other hand side, entropy is 1, maximum impurity is maximum impurity. Right? Similarly, we had also the other one, which is the Gini index. And this Gini index, the formula for Gini index was 1 minus summation pi. Pi is nothing but the proportion. Let me come to the case where you have got a case like this, which is a pure case. So then this is 1 minus proportion is 100 by 100 whole square. 100 by 100 whole square is 1 square. So it is 1 minus 1 equal to 0. Pure, no impurity, right? This is a very good variable for doing the splitting. If you use this particular variable, you are completely able to do the splitting. Vis-a-vis if it was the other case where there was a 50-50 chance, then this becomes 1 minus 50 by 100 square plus 50 by 100 whole square. Right? That's the corresponding proportion of the two classes. Good 50 out of 100, poor 50 out of 100. 50 by 100 is half. Half whole square is 1 by 4. Right? 1 minus 1 by 4 plus this one will also be half whole square, 1 by 4. The 1 minus 2 by 4 a half is equal to half. That's the amount of impurity which is there when you use a Gini index. Right? One note of caution is, please don't mix and match the different measures. Please don't say that, okay, the first step I'll use calculate the entropy, and then now I am feeling like using a Gini index. I'll now go to Gini index and calculate the impurity value, and then probably I'll do chi-square. No, no. Please ensure that you stay with the same measurement throughout a particular problem. If you're using entropy, please use entropy throughout the problem. If you're using Gini index, use Gini index throughout the problem. if you're using, let's say, the chi-square model throughout the problem. Right? Okay. I hope now if you go back and reread the slides, I hope things will be clear to you. Okay. Coming to the decision tree generation, we already discussed that what you do is first you take the data, split the data into training and this validation, and then what you do is that the first part of the data, whatever you're having for training, you build your model on the training part. Right? You do all these things. Find out recursively that which particular variable is most important for your problem. Work on it till the time you are arriving at a model which is able to make decisions for you. That's the training part. Now, come to the testing part. Again, one validation part. Here, this particular data is the unseen data. You have not seen it, the model has not seen the data. And then you have already built a training model. If your model is performing equally well on the unseen data or very good on the unseen data, then probably you have built a wonderful model. Otherwise, if your model is doing very well on the training data, but doing very poorly on the test data or on the validation data, then there is some problem with the model. What problem is there with the model? What problem is there with the model that you have built? The model does extremely well on the training data, but it does poorly on the test data. Then what's the shortcoming or the lacuna of the model? It is overfitting. Thank you so much. That particular case, the model is overfitting. It is able to reproduce the training data set well, but not able to do anything with the validation of the test data. Right? So that's why whenever we are doing a model evaluation, we do the model evaluation with the this testing or the validation. Right? That's what we try to do. There's a question from Kajal. How does information gain work with